I have a Cauchy sequence. And clear cut inputs. Cauchy sequence. Like that. This Cauchy sequence must be bounded. In other words, you can always find number which can kind of encapsulate all the number of the sequence within the big interval. Okay. If it is a Cauchy sequence, what should be true? It should be true that the distance between P and PL for any epsilon, no matter what epsilon you choose, is smaller than m, no matter what. Epsilon positive, I can find something there for which this is true. Now that we know that what should be done, switch a minute. I can show that yes, the sequence is. One of the hint is that think about the same way, the way we prove basically that every convergent sequence is bounded.
Sir, we can have it like take the before finite values which are n minus 1 values, take them and take the epsilon also. This epsilon, for any epsilon it's true. Choosing a maximum out of them would suffice.
Okay. Argument is going to be like that. We need to show basically more explicit. It's going to be one way or other way the same way. So let us fix this m to be capital N. So since this m can be anything, and this is true for anything, for all n and m, so this should be true also for n. Great. Then Pn minus capital N should be less than what epsilon for all n bigger than or equal to. So now this Pn is fixed vector. Okay. This Pn is a fixed number.
Smaller.
Smaller and bigger. So this Pn is a. Can I deduce? Give me the way basically I can deduce my label this that from this statement I can deduce that the magnitude of Pn is less than the magnitude of this Pn plus epsilon. And that's Pn is a fixed Pn actually for all n bigger than or equal to. In other words, after n, all of the terms of the sequences are bounded by this number. That's a fixed number. Because P at a fixed capital N is going to be one fixed number, not an arbitrary number. But I would like to see that how does from this expression I reach this expression.
Triangle reverse equality.
We will apply the reverse triangle. I can say that this is bigger than or equal to absolute of Pn minus capital N. Okay. And which is bigger than or equal to? Still I have trouble.
So what's the trouble?
But I know that epsilon, just like epsilon of this is bigger than or equal to absolute of Pn minus absolute of P capital. Yes.
Since the absolute is smaller, then
Exactly. So, as absolute is bigger than or equal to x for all x's. As this is true that absolute of x is bigger than or equal to all x, so absolute of this difference is going to be bigger than or equal to the number without absolute. And now I can say that yes, I can send this. Agreed?
Yes.
Make it more clear, that it should be visible. Then you can't have this set. You can't have that in epsilon. Then you're going to have Pn is less than capital Pn plus epsilon. While the definition demands that absolute of Pn should be smaller than or equal to the number. You can still have that why, because if the Pn is smaller than P capital N plus epsilon, just take the absolute on both sides and apply the triangle inequality on both sides. The easiest way is that you use this reverse triangle inequality. Pn minus capital P and this is bigger than or equal to Pn minus P. ठीक है? हमें for all n say. So like this inequality is true for all n bigger than or equal to.
now we'll take the
Now we're
finite.
going to do the precisely same thing. So I would like to have a set in which I have what? I
P1.
have-
Absolute of P1,
So absolute of P1
absolute of
and absolute of
P2,
after
Pn minus
absolute
1.
of P capital N minus
Minus
1 and
Pn plus epsilon.
capital Pn plus epsilon. And take the maximum of that and name that maximum
Is M.
as capital M.
So small.
The capital.
P8 minus
Capital.
Divided.
P capital N minus capital N is considered for all N
I'm saying that take all terms before this capital N and this number and take the maximum and that maximum is going to work. Why this is going to work? Just think about it. If this number is maximum among all these numbers, that means that this number is bigger than absolute of P2, absolute of P3 and all absolute of Pn minus 1. In other words, it's bigger than all numbers before and after. But since this is going to be also bigger than this number, so this absolute of P1 is going to be the bigger than all numbers in after capital N. So no matter what maximum is, okay, you're gonna have this inequality. That's you can say that for such an M, Pn is less than capital N for all n in the capital. Okay.
Sir, less than or equal to, because we have chosen the maximum.
Yes. This is true for all natural numbers. Okay. Actually, sequence. The next result that I'm going to prove is for the completeness of like to roughly define what I mean by complete metric space. I'm going to say that X is a metric space and it is complete if we take any Cauchy sequence in it, if every Cauchy sequence converges every Cauchy sequence converges in X. Now that's an important thing. That we not only need that every Cauchy sequence converge, but that converging limit must be in X actually. For example, based on this definition, I can say that Q is not complete. Because we have a Cauchy sequence, we can prove. Okay, one plus number and other hand. Okay, and its limit does not belong to Q. So it converges, but is not converging in Q actually. Hence, we can say that this is a space. So, we're not talking about in general completeness of metric spaces, but we're talking about the completeness of R. R is a completeness. In other words, I'd like to prove, you cannot say that to say that every Cauchy sequence converges in R. That's what one of the consequences of this result is that basically the gaps that we were saying previously we had in a rational line, okay, these gaps can be filled by the limits of the Cauchy sequence. Because okay, so the Cauchy sequences in rational numbers can have limits in rationals, but they can have also limits which are outside rational circle. Okay. So in other words, we can say that the gaps that we previously filled through radical and plus can also be filled through the limits of the Cauchy sequence. That's what this completeness theorem and the key theorem basically that R has this unique property. Because, okay, in other words, what we can say is this, that there can be two ways to answer this question. One thing is that I don't want to assume R, because for example, if I am saying that there is, so we have rational lines, imagine that we are in the same space. We have rational lines, okay, and we know that there are gaps in rational lines. So, now we say that if we define Cauchy sequences in rational numbers, those Cauchy sequences are going to converge. But they are going to converge outside rational numbers. So what we say that if they are converging outside rational numbers to some points which are not rationals, if you put those points into the rational line, you know that the line is going to be complete. So in other words, every real number is a limit of some Cauchy sequence in rational number. And that's what also the density means actually. So one of the interpretation of density of Q in R is that every real number is basically what is a limit of some Cauchy sequence or convergent sequence of this. Cauchy sequence. Every Cauchy sequence will converge, but not within a space, sometimes outside a space. For example, sometimes you say that you define convergence in this way. You say that a sequence is going to converge if you are able to find its limit, and that limit belongs to basically this space. So if it is not belonging to that same matrix space, you're going to say that it is not convergent actually. Every Cauchy sequence is not convergent in Q, but it is convergent in R. So let's talk. So see that beautiful proof from Slaughter books and information now. I didn't want it to get into Cauchy sequences that very early, therefore I wanted it to be there. But if you return now and see that beautiful proof, basically that how Slaughter is saying that the gaps in the rational lines can be filled by the limits of the Cauchy sequences in real life. So what is our task here in this theorem? The task is to prove that every Cauchy sequence converges. In others. We're going to say that let Pn in R, and I would like to prove that it must converge. Yeah. So in other words, the sequences, Cauchy sequences in R cannot go outside R actually, as they were going in Q actually. Therefore, you call it that's completeness. Everything is retaining within. So if it is a Cauchy sequence, can I relate some notion of convergence to this Cauchy sequence now, keeping in view the result that we have done?
It's bounded.
It is bounded as a convergent subsequence. So Bolzano-Weierstrass theorem says so that every bounded sequence must have a subsequence. So in other words, at least one thing that we can know immediately from this, that if Pn is a Cauchy sequence, there must be one sequence at least in that subsequence in this sequence which is convergent. My claim is that the Cauchy sequence is also going to converge to that limit, whatever the limit of that convergent subsequence is. So since Pn is Cauchy, so it must be bounded, and if it is bounded, so by Bolzano-Weierstrass theorem, there exists a subsequence Pnk, okay, such that this Pnk converges to some P as k goes to infinity. My claim is that Pn is going to converge to the same thing as n goes to infinity. Can you see this intuitively? Just think about it. You have this small ball, and since it is Cauchy, so all terms are going to stay within that, and within that, within that small ball and all terms of the Cauchy sequence, you have a subsequence which is getting closer and closer to some fixed point. And if you take that fixed point, and from within that ball, you take any other point, any other point of the sequence is going to be also, its distance is also going to be smaller than absolute. Are you getting the point? So it's like, I have this ball, so it's like the sequence falls in after the instant n here, and all terms are here. Okay. So in other words, the distance between all these terms is smaller than epsilon. So the Bolzano-Weierstrass theorem says that within this sequence, there is going to be one sequence which is kind of a convergent to a point. It's not necessarily at the center, but it's converging to some point at here. So in other words, distance between this point and all these terms is smaller than epsilon always. Okay? But since all of these terms are at distance smaller than epsilon from each other, so take any term and its distance is going to be also smaller than epsilon. So that's what essentially we're going to argue. What should I do? I would like to do this. I would like to have Pn minus I would like because I would like to prove this, so I need to take the difference between Pn and P and show that it's.
That's not the same problem.
I can write more precisely. Okay, if I need more precise, I can write more precisely. I can say for epsilon positive, there exists N1 and N2 such that G, the distance between Pn and Pm is less than epsilon for all n bigger than or equal to N1 because Pn is Cauchy, and the distance between Pnk and P is going to be smaller than epsilon for all n bigger than or equal to N2. Okay? So when both conditions are going to be true, so choose maximum of N1 and N2 and give it a name N. Okay? And give it a name N. And now consider En minus 2. What should I do?
Inequality triangle. Pn minus.
This Nk is going to eventually cross all numbers. Because Nk is always going to. Don't worry about that. So wouldn't that be an interesting idea that if I say Pn
Sir, can we say
and
since n and m can be anything, so can we say this m can be nk?
exactly, that's precisely what the point is, that you take the Pnk plus Pnk okay, and minus what? Triangle inequality, so Pn minus Pnk plus Pnk minus P. It's epsilon by 2, epsilon by 2. Have got results provided that this Nk is bigger than or equal to N. So we're going to say that for sufficiently big N. So if this Nk is going to eventually cross this N, then the distance between Pn and Pnk is going to be less than epsilon by 2. Less than epsilon by 2. Epsilon. End of the story is. Okay. One of the reasons that I chose, especially for sequences, this book was that Rudin is giving basically limited number of results, not talking about too many results. But the second thing is that he's talking in musical spacing. While there is no need that at the moment we should indulge in too much musical spacing, especially in the sense of convergence, while we have to just learn things in our time. ठीक है, is it like get rid of something. So we're not going to cover anything else from this, and we are going to get now gradually, at least I would like to define and do some basic results about the series. So I'd like to begin with the series. Here we talked about the convergence of sequences. Now I'd like to talk about the convergence of series. More than one or two lectures in this chapter. Then we'll jump into the calculus. If you, for example, are following these properly, there's lots of stuff on that. In the sense of examples, in the sense of results. And the second thing is that, we most of the time are not interested in the things which we can't make sense of. If something that's coding is not of our practical use, right? We are interested in it. But it is also good. Sometimes, I'm not saying that divergence is not, it's extremely important. Because it's a way to understand convergence. Sometimes you understand and recognize things from their opposites. You want to understand the meaning of something, think about its opposite. Focus was on convergence solution. Let's move ahead of the series. I hope that you might have done previously for a sample series, so you know basic stuff that how much of series we have done basically in calculus course this. We didn't done it. I know that. Okay. In calculus, some ratio test and the limit test and the comparison test. Okay, something like that. In this discussion, what we are going to do is to prove all those results. Know the use, we're going to use them obviously. We are interested in the legitimacy that these are not something God given. We can actually prove something. Okay, the series stuff, for the series stuff, we will be back to the review. We're going to do it from this. Rudin, series will not going to follow. Okay, so let's move to series.
Let's work the seeds.
Okay, so what is our, why series are interesting actually? Why series are interesting still? You might have already seen some bits in probability theory especially, for example, that if I have a series of random quantities and roughly it converges to something which is, so it's like if I have a series of random variables, okay, follow such distributions, then there is some convergence to, so it behaves nicely, so it behaves like the standard normal distribution or the normal distribution. Okay. So we can already see that the series are are a very good tool to have some of the key information. Have you done some of Fourier series?
Last two.
It's like that what you practically do, for example, that okay, you have starting signals. It's like I have a, let's give this example on that, but at least you must have done the Taylor series or
Yes, sir. Taylor,
Clarence series.
you are